Welcome back, everyone. I hope you enjoyed the coffee break and are ready to continue. So our next session will start with Sara Pasquetti, who's going to tell us about mirror dualities with 4 supercharges via the improved algorithm. Please go ahead.
Okay, thank you so much. Thanks to the organizer for setting up this very nice meeting so far, very nice. So I would like to present some work done in collaboration with Sergio Benvenuti from SISA and Riccardo Comi, my students from Milan. So the problem that I want to address is that of infrared dualities. Of course, infrared dualities, since the discovery of cyber duality mid-90s, have been proliferating. So we know by now a plethora of dualities in various dimensions interconnected by different RG flows. And some people are asking a series of questions about these dualities. Maybe if it's possible somehow to organize the space of dualities, whether we can find an organizing principle, or maybe whether we can prove that all dualities have a stringy origin. In this respect, this is a very active research area, and people like Shlomo Razamat and Gabi Zafir have contributed a lot to this sort of geometric approach to dualities, where dualities emerge as consistency conditions for different compactifications of higher dimensional theories. Another type of perspective that I want to address today is instead whether it is possible to study dualities purely in field theory and maybe to prove that all the dualities can be demonstrated in terms of a small set of more fundamental dualities. And there are indications that something like this can be functioning in the sense that we now know that large families of dualities can be derived, indeed, assuming only a small set of elementary dualities of cyber type. So this is, we have basically 2 types of approaches. One is the so-called sequential deconfinement. It is an old idea dating back to Berkutz in the mid-90s that has been revamped in recent years. And by now, thanks to this type of dualities, we can, for example, prove all the S-confining dualities that were classified in the 90s, and other type of self-dualities for theory with tensor matter. And there is also now some update that we are going to put out for Kutazo-Schwimmer-like dualities. And today, instead, I want to focus on another type of dualities, which are mirror dualities, for which we propose an algorithmic approach, which also provides a demonstration, a field theoretical demonstration of these dualities in terms of cyber dualities. So let me say a few words about mirror dualities. These are dualities for theories with 8 supercharges in 3 dimensions, and it relates pairs of theories where the Higgs and Coulomb branches are swapped. So the first simplest example is the abelian mirror pair for the U1 theory, the super QED with 1 hyper, which is mirror dual to a free hyper, which can be exactly understood in field theory as a sort of a functional Fourier transform, where you transform the partition function of a free hyper depending on a background vector multiplet for the U1 flavor symmetry that is then transformed by an action which is just the BF action. And it returns the partition function of an hyper coupled to a dual U1 flavor symmetry. So thanks to these abelian fundamental dualities, you can demonstrate, as observed by Kapustin Strassel, all the abelian dualities. So in this case, we have a complete field theory understanding of this duality. But if you want to understand non-abelian dualities, then we often resort to their geometric realization in terms of branes and their stringy origin. So indeed, for 3D theories with 8 supercharges, we have Anani-Witten brane setups, and where you realize these 3D theories as the low-energy theories on a setup with an S and D5 brane and D3 brane suspended. And in this case, mirror symmetry in field theory is understood as a consequence of the S duality acting on the 5 branes in type 2B. So here is the classic example. You have the SQCD with n equal 4 in 3 dimensions. So here I'm using an n equal 2 notation. There is an adjoint which sits in the vector multiple, and multiplet is coupled to the hyper, to the positive and negative charge chiral. And it is realized as N2, NS5, and F, D5 branes. And S duality acts on the brane setup swapping D5 and NS5. Then there is some rearrangement of branes, and you can read out the mirror theory, which is a complicated quiver theory. So once, if you want brane setup suggests you this duality, you can go ahead and test it in field theory. So you can do as many tests in field theory as you want once the duality is stated. For example, you can work out the operator map. So classically, you can observe that the mesonic operators, so operators that are charged under flavor symmetry, are mapped to monopole operators that are charged under the topological symmetries of all the nodes. And vice versa, you can see that monopole operators of the electric theory are mapped to mesonic operators in the magnetic theory. Then you can go ahead and make even more modern tests. You can test partition function, indices, and all is good. All is amazing. And you can see very well also the map of the fugacities for the global symmetry. So you see, for example, that the real mass parameter for the flavor symmetry are nicely mapped to the Fayette-Yoplus parameter in the dual theory. So of course, you can convince yourself that these dualities are completely true in field theory, but is there a field theory derivation of such dualities? And to answer this question, we devised this algorithmic approach with Qin Wang and Matteo Sacchi starting from a few years ago. So the idea of this approach is that we want to implement at the field theory level the action of S-duality. So the action of this duality that I mentioned before says that S-duality acts by swapping NS and D5 branes, but you can think that this action is actually local. So you can dualize individually each 5 brane. So you can think that you are dualizing individually each 5 brane. So the procedure of the algorithm consists in implementing this local action at the level of field theory, and it begins by taking your theory with A supercharges and chopping into what we call QFT blocks, which we associate to the NS5 branes with D3 branes ending on each side. So there's going to be, of course, what we call the bifundamental block associated to an NS5 with D3 branes ending on each side, and a block that we associate to the D5, which instead is just a flavor block multiplied by this gadget here, which is just an identity wall, which identifies the two non-abelian symmetry rotating the two sets of D3 branes. So for example, going back to the example of the QCD, this is how you break up the QCD into QFT blocks. So you have F fundamental block, as many as the flavors, and then you have 2 bifundamental blocks that are associated to the NSs. Then the second step of the algorithm is really implementing the action of the S-duality. So you want to implement at the field theory level this operation of dualizing a D5 into an S5, and this action is represented by these genuine infrared dualities. So on the right-hand side, you find the theory of a bifundamental, and the left-hand side instead is a more complicated theory where you have in the middle a flavor block, and to the sides you are gluing an S-wall, the S-wall theory, as defined by Gaiotto-Witt and known as the TSUN theory. So this is a theory, it's a complicated quiver theory that satisfies, if you want, various relations, which are dualities. Like if you fuse 2 of these theories with a flavor in between, you get basically a Versumino model, which is represented by this duality move, we call. Another non-trivial properties of this theory is that if you fuse together 2 of these S-wall theory, you get the identity wall. So the second step of the algorithm is to go and dualize each of the QFT block in which you have broken up your theory using this basic S-duality move. And then there is a third step on which today I don't have time to discuss much, but it's once you have done this operation, typically you are left with some expectation value turned on, so you are supposed to study the RG flow into the final infrared theory, and this operation can be implemented in field theory using what we call the Anani-Witten duality moves. These are, again, genuine infrared dualities, And they are, if you want, the counterpart of this operation that you do on the branes of rearranging the branes to avoid S-rule violations. But all these operations have perfect sense in field theories as infrared dualities, and they can be proved assuming only cyber dualities. So summarizing what the algorithm gives, it's a purely field theoretical proof of mirror dualities, assuming only cyber dualities. So you no longer have to resort to a stringy construction to conjecture dualities. You can prove it, assuming only a fundamental field theory duality. I described this procedure at the level of field theory blocks, but you can implement this procedure at the level of indices and partition functions. So this is a procedure that generates for you integral identities between these exact quantities. And a bonus is that this procedure gives you the exact map of all fugacities and all the background Chern-Simons coupling that you have to add to dualities so that they are properly defined. So there are generalization of this idea of the algorithm. We extended the algorithm to generalize SL2Z dualities for theories with n equal larger than 3 and Chern-Simons coupling. We run the algorithm for bad theories. So bad theories are theories bad in the sense of Guyot and Witten are theories where you find operator, typically monopole operator, that are below the unitarity bound. And this type of theories, they are quite subtle because they have a decoupled sector. And in particular, the partition function for this theory is ill-defined, so it's a divergent object. So our analysis based on the algorithm for bad theories shows that the partition function is actually a distribution. It's a complicated gadget. It's a distribution, and the support of this distribution is at points where you have good theories. So in a sense, the theory can be regarded as a sum of good theories of smaller rank. However, today I want to discuss another direction in which we have extended this algorithmic approach, which is in the case where we have less supersymmetry, so 4 supercharges in 3 dimensions. So here the situation is a bit different. So I hope I passed the message that if you have 8 supercharges, people knew very well how to construct a mirror dual using branes. And so our procedure is more like try to prove it also at the field theory level. But in this case, 4 supercharges, brane setups are not very helpful. If you try to study a mirror, an S-dual pair of brane setup with 4 supercharges and read out theories, you get typically what we call naive mirror pairs. And naive is in the sense that the theories that you get, they don't have the symmetries that are supposed to have. So you have a time in matching the symmetries on the 2 sides of the duality. So something somehow is missing, and this construction with branes is not very informative. So how do we improve on that? Well, what we try to do is to run, to improve the algorithm for the case with 4 supercharges. But to do so, we need new ingredients. So we need the new QFT blocks and the new duality move. So the first gadget that we're going to need is an improved bifundamental block. So this is the first conjecture. So we claim that the new object that we need to associate to a theory related to setups with 4 supercharges are not ordinary bifundamentals, but these gadgets, improved bifundamentals. So these are strongly coupled STFC. They have a UV description in terms of quiver theories. Notable features of these quiver theories that at each node you have a monopole superpotential, so you turn on linearly the fundamental monopoles. This theory has 2 non-abelian symmetries. One is manifest, rotating the flavor, the mesonic operator, and one is emergent, rotating all these U1 symmetries in here. But we represent it in a compact form with this double wiggle line. And this theory, importantly, in the spectrum has 2 operators, like moment maps in the adjoint of the UN non-abelian symmetries. And then it has 2 operators in the bifundamental. So this is why we call it the improved bifundamental of these two UN symmetries, plus some other singlets that are only charged under the abelian symmetries. And there is a mirror duality, which is swapping these two non-abelian symmetries. Now, interestingly, this theory, this improved bifundamental, sits inside a larger family of bifundamental blocks, which we are studying, and they all descend from a mother theory, which is a four-dimensional FUSP2N theory. Probably you heard about this in some of my talks, but it appears also in the construction of the A string. So interestingly, this gadget, this improved bifundamental, has some limits. So you can turn on a deformation, a superpotential deformation, typically turning on some of the singlets charged under the abelian symmetries. And the effect of two of the most interesting deformation is to basically Higgs down this theory into the ordinary bifundamental. But you can further Higgs it down to a theory which is the identity wall. If you want, it's like going to a theory which is confining to a theory with quantum deformed moduli space. So this is this singular theory, which is like a delta-like function identifying two sets of global symmetries. In addition, you have instead real mass deformation, which can turn this generalized bifundamental in either the TSUN theory I mentioned about, the TSUN duality wall, plus some background Chern-Simons coupling, or into a new gadget that I will mention later, which we call improved chiral. And as the name suggests, this is another bifundamental where in the spectrum you have only chiral operators in addition to the adjoint operators. So this was the building block, and now we need the new improved basic move. So we claim that if you have an n equal to flavor, so now it's important this, notice that in this case, the flavor I'm drawing as a chiral, fundamental and anti-fundamental chirals, because they are not coupled to the adjoint. So this is generally an n equal to chiral, and it has this feature of the flavor doubling. So chirals and fundamental and anti-fundamental chirals rotate independently, so there is more symmetries in a theory with n equal to supersymmetry. And it is, when acted by, from the left and on the right by the S-wall, it transforms in this gadget that we name improved bifundamental. So this is what replaces, okay, the dualization of a fundamental into a bifundamental. Indeed, if I turn on an n equal 4 deformation and I include these two chirals into a superpotential with a joint, the effect on this side is to iron this gadget into an ordinary bifundamental. And then we go back to the algorithm for theories with 8 supercharges. Now, again, also this non-trivial duality is an infrared duality that you can prove this time with more effort, and is going to appear soon, using cyber dualities, basically. And these type of relations are part of a family of star triangle or braid dualities, which can all be generated assuming only cyber dualities, and they have roles in this type of dualities for quiver theories. Okay, so having defined the new block and the new basic moves, I can start from an n equal to SQCD. So now you see I have a UN theory with F chirals and F chirals of charge minus, fundamental and fundamental, no superpotential. So this theory has 4 supercharges. I claim that the mirror dual that I obtained by running the algorithm base of this generalized improved n equal to move is a theory where you have, instead of ordinary bifundamentals, you have these improved bifundamentals. So it's not a Lagrangian theory, it's a quasi-Lagrangian theory because you have to gauge emergent and manifest symmetries of these new blocks that constitute the improving of the bifundamentals. So here in between, I'm just rewriting the electric theory, reorganizing chirals, fundamental and anti-fundamental chirals into, say, hypers, but I'm keeping track of the symmetries. So there is going to be xi, which will be vector-like symmetries, and bi's, which are going to be axial symmetries. I'm just repackaging the two UF and you have symmetries rotating the two sets of chirals. And now you see pictorially how the symmetries are mapped. So these vector-like symmetries are being mapped to these symmetries that are topological symmetries. I'm using this bracket to denote a phi parameter. So as expected in a sense for mirror dualities, vector-like flavor symmetry map to topological symmetries. And now you have more symmetries. You have these axial symmetry. They map to some of the extra billion symmetries that are carried by these improved bifundamental. So that's the main thing, that now we have a dual, mirror dual for QCD, where all the symmetries are correctly reproduced on both sides of the duality. So you can realize the symmetries, which is UF times UF non-abelian symmetry, and all the abelian symmetry on both sides of the duality, which was not possible with a naive construction inspired by brain setup. So you can test this result from the algorithm in various ways. You can work out operator map. Of course, you can see that mesonic operators charge under the vector-like symmetry map into monopoles, and then somehow these components of the meson matrix that is only charged under the axial symmetry map to singlets operators containing these improved bifundamentals. You can check that monopole operators of the electric theory instead map into long mesonic operators that you construct chaining all these improved bifundamentals. So, and here is the observation that I make, that vector-like symmetries indeed are mapped into topological symmetries and axial symmetry into themselves. Various other consistency check. You can start integrating out some flavors and observe that in the mirror dual, the length of this this quiver becomes one less unit. You can turn on n=4 deformation, making your theory becoming the n=4 SQCD, and consistently observe that the mirror dual with improved bifundamental reduces to the expected n=4 mirror dual. If you have this n=2 mirror pair, you can also start playing with real mass deformation and generate theories with Chern-Simons coupling. For example, you can integrate out, imagine that I start the theory with 5 fundamental and 5 anti-fundamental chirals, so the dual has 3 generalized bifundamental link. If I integrate out a chiral of charge plus and charge minus, I generate a Chern-Simons level, and the claim is that in the dual theory, we replace one of these improved bifundamental with a TSUN link. Instead, if I integrate out only, say, an anti-fundamental chiral, I land in a theory with a half Chern-Simons unit, and one of the improved bifundamental is replaced by an improved chiral. So we can describe mirror dual for generic Chern-Simons matter theories. So just a comment, what is this fundamental chiral? This is going to appear soon, is another of these elements in the families of generalized bifundamental theories, is described by these quiver theories. We are in 3 dimensions, n=2. Each node has a monopole, single monopole superpotential turn on, and crucially now in the spectrum you find just a bifundamental chiral rather than a chiral and an anti-fundamental chiral. Okay, so let me come to brains. So in the case of the theory that we have been discussing, so the joint n=2 SQCD, we do have a tentative associated brain setup with 2 NS5 and F D5 prime. So this is a setup with preserving only 4 supercharges. Now NS and D5 prime, they have 2 directions in common and they can web. So this is why you don't have a superpotential on this side, and you have the flavor doubling. Now, if you act with S duality on this setup, this is what you get. This is S duality actually combined with a rotation. So NS should go in D5 prime, but I draw it as a D5 just for convenience. Now, so this is the S dual setup, and this is the mirror dual as I created from the running of the algorithm. So these two theories should be related. So this should be the low energy theories living on this setup, and setup with 4 supercharges. So what we seem to learn from this is that if you want to describe a brane setup with 4 supercharges, you have to replace your bifundamentals with this gadget, these improved bifundamentals. So starting from here, we develop a set of rules on how you read a setup with 4 supercharges. So this is an example, 3 NSs and some D5 branes in between. So in particular, we have to attach improved bifundamental to any NS5 over which the D3 strings stretch. Now here, notice that on the electric side, you have a large non-abelian flavor symmetry. You have SUF1 times SUF1, because you have flavor doubling, and SUF2 times SUF2. Now, these symmetries on the mirror side are interestingly emerging because you have string of improved bifundamental. And we observe this, if you construct string of improved bifundamental, they basically produce an enhanced symmetry in the infrared. So this is, in a sense, a generalization of the notion of balanced node in the 8 supercharges case. In the 4 supercharges case, if you have a string of balanced node connected by improved bifundamental, there is also an enhancement of global symmetry. And of course, so the way we test this proposal, so we came up with a set of rules on how to associate a theory to this setup, how to associate a theory to this S-dual setup, and we check that these two theories are dual as field theories by running the algorithm. Okay, so coming to my conclusion, so we have developed an improved algorithm to prove mirror dualities with 4 supercharges, and including theories with Chern-Simons coupling. And we have also developed a 4-dimensional counterpart of this story. So we have an algorithm to construct mirror dual of 4D n equal 1 theories. In particular, we have the mirror dual of USP2N SQCD. So in addition, say, to the cyber-like duals for these 4-dimensional theories, now we can construct also mirror duals. So a feature is that we think that these theories are associated to brane setup with 4 supercharges, and our proposal is that in these setups, we should use this improved bifundamental rather than ordinary bifundamentals. So far, we only study setups with constant number of D3s, but it's just the beginning, because we need to allow non-constant numbers of D3s and all 4 types of branes simultaneously. So we still have to come up with the rules to describe these more general systems. So now, you see, I'm extended even more the network of dualities that can be proved in terms of basically only cyber-like dualities. So I come back to my original question, whether there are other infrared dualities which cannot be explained in this term in terms of more elementary dualities. And the question remains, do all dualities have a stringy origin? So in the case of 8 supercharges, it was the type 2B realization that was giving a lot of mileage on the field theory side, but here the logic is reverse. Now we made progress on the field theory side, but we are still missing on a stringy or brane interpretation or geometric interpretation of this improved bifundamental gadget that we need to use to match the symmetries in field theories. And of course, big question ahead, what about non-supersymmetric dualities? We know that most of these dualities are related to bosonization. Can we make this more precise? I'm done, thank you.